Hello, this is Rick from MathX, and since our Corona break is only going to be extended probably throughout all of summer, we should use this time to learn something new. We want to keep our brains fresh, so when the new school year starts again, we're going to be right on top of things. And today, the concept video that I want to go over is finding the area of a triangle. Now, before you start laughing and leave the video, finding the area of a triangle is not always as easy as you think. Sure, most people know one or two formulas and think they know the whole concept, but finding the area of a triangle can be done in a multitude of different ways. And there's a reason why, even though this concept seems quite simple to begin with, lots of high-tier competitions like AMC10 and AIME request for you to find the area of certain triangles. Because even though we know a couple formulas to solve for the area of a triangle in one way, not all problems will give us the same information. So to be able to adapt and to solve for the area of a triangle no matter what information we're given, I'll be making a list showing you 5 different ways to compute for the area of a triangle. Now, I've decided to split this up into a 5-part series because if you don't want to learn all these ways, as some of them you may already know, or some of them are just too advanced for you, you can always drop out of a video and maybe just watch the videos that apply best to you. But in this first video, I'll just be going over the basic way, which is a way hopefully all of you know. But I'm also going to be doing an example problem, so stay tuned for that. So let's start. This first way I'm going over is probably the easiest way, and most of you guys should already know this already. The formula we'll be using to compute for the area of a triangle is area is equal to 1/2 base times height, where A is the area, B is the base, and H is the height. And most of you should know this formula, as it's taught really early on to most students. And while most students get the hang of this formula pretty quickly, what not all students grasp as easily is that a base and a height, well, any side could be the base of a triangle. And each of those sides has their own respective height. But the one thing that these bases and heights must have in common is each of these bases has to be perpendicular to its respective height. So if we take a look at this right triangle here, with one leg of B, another leg of A, and the hypotenuse of C, we see that if we take A as the base and B as the height, we can compute for its area like this. Area is equal to 1/2 base, which is A, times B, which is height. However, we could just as well take B as the base and take A as the height, in which case the area would be 1/2 B, which is base, times A, which is the new height. But that's not all. If we take C as the base, we can draw in our own height and label it H. And doing so, we can compute its area, just like the rest of them. C, which is the base, times H, which is its height, which is perpendicular to it. And half of their product gives us the area of this triangle. So, even though this formula looks quite simple, with base and height, in any given triangle, the bases could be any of its sides, and the height is whatever length perpendicular to it from the opposite vertex. So this will often come up on an AMC10 problem, where it'll ask you for like the smallest height of a triangle, or the largest height of a triangle. And because we see that these bases and heights will multiply up to twice the area, the base and the height of a triangle are inversely proportional to each other. So that means if one of them will increase, like let's say we have a larger base of a triangle, we need a smaller height to compensate for the same area. So you can use this idea to help you solve many AMC10 problems and beyond. Now, in a right triangle, we can typically identify at least one base and height pretty simply just by looking at where the right angle lies. We can also do the same thing with an isosceles triangle. As if you have an isosceles triangle and you draw an altitude, well, the altitude of an isosceles triangle to the non-equal side will bisect that side. So in this case of this 5, 5, 6 isosceles triangle, this 6 side will be bisected into a 3 and a 5. And since we know it's an altitude, that means that this side, and this side will all be subject to Pythagorean theorem, meaning that this side, which is now 3 because it's been bisected by the altitude, plus this side, which we don't know, well, the sum of the squares of each of these will give us 5 squared, because that's just how Pythagorean theorem works. So 3 squared plus x squared is equal to 5 squared. Doing the simple subtraction and keeping the x squared on one side and the 5 squared and 3 squared on the other side, we see that x squared will equal to 16, meaning that the only two solutions for x are 4 and negative 4. And of course, since we're doing geometry, the height cannot be negative 4. So we find the height to be 4. So just like that, we found the height of this isosceles triangle, and we already know the base to be 6. So we can compute its area as such. Area is equal to half of base, which is 6, times height, which is we found to be 4 using Pythagorean theorem. So we find the area to be half of 6 times 4, which is 12. So this simple formula, area is equal to half of base times height, can automatically give us the area for two different types of triangles. Just like that. If we have a right triangle, we can automatically identify a couple of bases times heights. And if we have an isosceles triangle, we can drop an altitude in to create a height. And since we know that an altitude of the non-equal side of an isosceles triangle bisects the side, we can use some simple Pythagorean theorem to deduce the height. But along with that, we can find it for other types of triangles. Because this formula is applicable to any sort of triangle. So let's say we take the scalene triangle and we know the base and the height. We can just compute the area just using the formula. So this simple formula can already get us a long way. As long as we remember how to use it, and that any side can be the base, as long as the height is perpendicular and comes from the opposite vertex. So let's try an example problem. So this example problem comes from the number 14 from the AMC of 2014. And it says, rectangle ABCD and right triangle DCE have the same area. And these figures are joined to form a trapezoid, as shown. And then the question is asking us, what is DE? So it tells us that this rectangle and this triangle, they both have the same area. So if we find out their common area, well, then maybe it'll help us find out the side lengths of the triangle. So since both of them have the same area, if we just find out the area of the rectangle, we already know the area of the triangle. We see that the base of this rectangle is 6 and the height of this rectangle is 5. And since this rectangle is basically two triangles over a common line, to find its area, we just need to multiply base times height, giving us that the common area is 5 times 6, or 30 in this case. So now that we know that the area of this rectangle is 30, we know that the area of this triangle is also 30. But here's the thing, we also know a length of DC. Since this is a rectangle, AB and DC both share the same side length. So if AB is 5, DC is also 5. And this means by using the simple base times height over 2 formula to get the area, well, we already know the height and we already know the area. So if we can set up some algebraic equations to solve for the base. So the algebraic equation we can set up is 1/2 times CE times 5 is equal to 30. And this is just the classic equation, 1/2 base times height. In this case, we know the height to be 5, and we don't know the base. We just express it as CE. So then if we just solve it algebraically, we get CE to be 12 by multiplying 30 by 2 and dividing by 5. So now we know what DC and CE are. And we know that it's also a right angle triangle because it says that in the problem. We can also see the right angle sign here. So that means this triangle follows Pythagorean theorem. So we can use that to find out the length of DE. So Pythagorean theorem will state that DC squared, which we know how to have a length of 5, plus CE squared, which we know to have a length of 12, will equal to DE squared. So substituting the lengths into the typical Pythagorean theorem equation, we get 5 squared plus 12 squared is equal to DE squared. So when we add that and take the square root, we find DE to be 13, which will give us an answer of B. So just by using the simplest formula out of the bunch, we've solved an AMCA problem, showing how crucial knowing these formulas are to do well in any sort of competition. So this concludes the first video of this series I have on areas of a triangle. And I hope you tune in for the next one, in which we explore Heron's formula and its applications to find the area of a triangle. Thank you for watching, and tune in next time.